We're given a mass that's suspended from a spring. Then the spring is compressed a distance of 4 centimeters, so it's pushed in other words, pushed up if we're hanging it from the ceiling. And then it's released. The mass returns to its compressed position after 1/3 of a second. Okay, that's a complete cycle. Find part A, the function that models the mass displacement, simple harmonic motion, because we don't have any damping here. Part B, sketch the graph of the mass displacement. Now, I want you to notice that when we begin in a compressed position, the A value is going to be positive. When we begin in a stretched position, the A value would be negative. Okay, and otherwise I would have to tell you if we started at 0 whether you assume it's positive or negative. So we know we're starting in a compressed position, so we know that the A value is going to be positive for this guy. Okay, so let's see. Another thing to recall, amplitude is 1/2 y max minus y min. And we're going to apply that a little bit later when we do the sketch. Okay, back up to the top. Let's start with step 1. Step 1, since the mass does not start at 0, we have to decide which of the two equations to use, the sine or the cosine version of the simple harmonic motion. Well, since it does not start at 0, but it starts at absolute value of A equals 4, we use the cosine version of the simple harmonic motion equation. Y equals A times the cosine of omega times t. Step 2, find A. Well, we started in a compressed position. That's what we were told. Started compressed, and I just got through telling you if you start compressed, that implies that the A value is going to be positive. So that implies A is greater than 0. Okay, so we know the absolute value of A is equal to 4. Therefore, the A value is equal to positive 4. Okay, step 3, find omega. The definition of the period is T period, T equals 2 times pi over omega. So let's solve this. Well, wait a minute. We know the period. It returns to its original position in 1/3 of a second. So period T is 1/3. 1/3 is 2 pi times omega. Just solve that equation for omega. Omega equals 6 pi. Step 4, thus the equation of motion is, just plug in the values, y equals, okay, in place of A, we're going to use positive 4 times the cosine of omega 6 pi times t. That's our equation of motion. And it has a frequency, by the way, of 1 over t. We found, we knew that t was equal to 1/3, so t is going to be 3 cycles per second. It repeats every second. It repeats 3 cycles. It completes 3 cycles. Step 5, let's do a sketch of this guy, and let's see, we're going to have our y-axis. It's going to be displaced from -4 to +4, and we're going to consider time all the way through from 0 to 1/3 of a second. Okay, so we'll go 0 to 1/3 of a second, and we know it starts at time, so the period is 1/3 of a second. That's why we decided to go from 0 to 1/3 of a second to do one complete cycle, one period. We start in the compressed position at 4, so we put the point at 4, and then we come down. We're going to be at -4 at the midway mark between 0 and 1/3 at 1/6, and then back up to +4 when we go all the way back up to the end of the period, 1/3. And we hit the y-axis. We actually hit the x-axis at 1/12 and 1/4. And what you want to recall is that the amplitude is half of y max minus y min. So in this case, the amplitude is 1/2 times 4 minus a -4, and that would make it, let's see, half of 8 is 4. So the amplitude is 8, which agrees with A, capital A being equal to the absolute value of A, which is equal to 4 units. So put a little check mark right there, 4 units. And we're done.